Hello, welcome to my talk on basic potential flows for potential flow theory. In this talk, I will present the simple potential flows for which we will see what are the potential expressions, and we will see the corresponding equipotential lines and stream lines in 2D cases, which would provide us the good pictures on the fluid patterns. Then we further talk the combinations of the simple potential flows and how we can use the singularities to represent the structures in fluid. These simple potential flows are extremely important because they are the foundations for the famous panel method for fluid structure interaction, and we have seen many applications in both aerodynamics and hydrodynamics. In the first part of the talk, some very important potential flows will be discussed, including the uniform flow and the flows of the singularities. At this part, we'll focus on the mathematical expressions and the fluid patterns, as well as the significance of the flows. The simple potential flows include uniform flow, the flow of a resource or a sink, the flow of a source-sink pair, the flow of a doublet or a dipole, and the flow of a vortex. Uniform flow can be said the simplest flow. It is a very important flow and the fundamental flow in the potential flow theory. Here, the uniform flow is taken as the velocity of u0 in x direction. See the picture here. The fluid potential of the uniform flow can be simply given as this, and the corresponding velocity component can be calculated as this. Here we can see only one non-zero velocity component, u, is along x-axis equaling to u0. Now we can check the relations. We can see here the uniform flow satisfies the Laplace equation as well as the continuity equation. And we put all this together because these two relations are linked together since Laplace equation is derived from the continuity equation for incompressible flow. We can also check the core of the velocity vector v, calculated as this. And here we must note that the differentiation of the velocity component with regard to z would be 0. Thus, the determinant would be given as this, and here we can see the core of the velocity vector is 0. Hence, we can say the uniform flow is the potential flow. We can use the definition of the velocity component based on the stream function given by this. And we can easily solve the equation so we can obtain the stream function expressed as this. Now we have both the expressions for the potential function and the stream function. For the equipotential lines, the consistent potential function would be given by the consistent x. So we have the vertical lines for the equipotential lines. the stream length would be given by the constant stream function psi, which would be decided by the constant y. Thus, the stream length would be horizontal. So if we draw the equipotential lines and the stream lines, so we can see here the equipotential lines phi 1, phi 2 to phi 6, and the stream lines psi 1, psi 2 to psi 6. And these equipotential lines and the stream lines are orthogonal everywhere in the uniform flow. And this is guaranteed because in 2D, the dot product of the gradients of the potential function and the stream function would be 0, as we have proven in the last talk. The uniform flow are very simple, but yet very important in the potential flow theory. In reality, only few uniform flows are existent, such as the flows in wind and water tunnels. And in applications, we might have many equivalents of the uniform flows. That is, based on the Galilean invariant principle. See the equivalent representations of uniform flow. In reality, the airplane flies in the calm air. It would be equivalent to the stationary airplane, but the airflow with the same speed coming to the airplane. So this is the principle we can do the experiment as well as in the computations for the flow past the airplane. Based on this principle, we have many different applications. The vehicle travels on the road or the trains on the railway. The ships travel on the calm sea. And in some cases, the sinusoidal flows, like the ocean waves, can be also simplified as the uniform flow. In reality, the flow can be given as this. However, in frequency domain, we can drop the time factor here, so we actually have the uniform flow in frequency domain. And many more examples. In this slide, the flow of a source or sink will be presented. Consider a source with the flow rate capital Q at the origin. And in 2D, the velocity potential function would be given in this form, and the corresponding velocity components are calculated by these expressions. So if we calculate the velocity gradient with x and with y, we have this. So we can check the Laplace equation and the continuity equation are satisfied for the flow of a source. For a sink, all the mathematical expressions would be same, only the flow rate, the capital Q, would be a negative value. And in 3D, the potential function for the source would be given by this expression. Based on the velocity component here, we can calculate the partial differentiation u with regard to y given by this, and v with regard to x given by this. And we can obtain the core of the velocity vector into d given by this, it is 0. This means the flow of a source or sink would be an irrotational flow. Now we write the potential function in polar coordinates. Phi would be given by this. And for a constant potential, we can see different r would give different constant potential. Based on the gradient of the potential function in the polar coordinate given here, so we can calculate the radial velocity u r and the tangential velocity u theta given by this. And based on the calculation, we can also build the equations for the stream function in the polar coordinates given by these equations. And we can easily solve the equation for the stream function given by this psi. So we can see here, for the constant psi or the stream function, we can see for different angle coordinates theta, we get the different streamlines. So if we draw out the equipotential lines and the streamlines, we can see this is the plot for the equipotential lines and the streamlines for a source. And again, we can see the equipotential lines and the streamlines are orthogonal everywhere. The third example is the combination of a source and a sink, that is, source-sink pair. The distance between the source and the sink would be 2a, see here. And the potential would be calculated using the superposition of the potential for the source and the potential for the sink. So we can calculate the potential for the source-sink pair as this, and further write the potential function as this. So in reality, the source-sink pair is not very useful, since we have to specify both the source-sink strength Q as well as the distance A here. This is not convenient for an application. However, one of its special cases would be very useful when the distance A becomes infinitesimal. In that case, the source-sink pair becomes a doublet or a dipole. So the fourth example is for a doublet, which is the source and the sink pair, but the distance between these two singularities are infinitesimal, means A close to 0. And the potential would be calculated as this. However, since A is very small, so we can further calculate the potential as this. And we can obtain the function as this. Now we can drop the high order of A, the small value, so we can have the approximation for the potential function as this. Here we continue the derivation of the potential for the doublet. In this expression, we are trying to make the term with A in the denominator become a higher order term. So we make the expression as this. And we have the expression as this. Here we can see this term would be high order term for A. So we can simply drop this term. We have the expression as this, and it is equivalent as this. Now we can apply the approximation given by this if theta is small compared to the unit, as we have seen here. When A is small, so this term would be very small compared to this unit. Therefore, we can obtain the expression for the potential of the doublet given by this. And the potential function for the doublet can be written as in this form here. Mu equaling to 2aq would be the strength of the doublet. And in this expression for the doublet, we only have one parameter, the strength of the doublet. Similarly, for the 3D, the potential function for the doublet would be given in this formulation. For the potential of a doublet, we can write the potential in the polar coordinate given by this. And we can calculate the radial velocity UR given by this, and the tangential velocity U theta given by this. So based on this, we can build the equations for the stream function. So this are given as this. And from these equations, we can solve the stream function psi as this. And if we draw the equipotential lines and the stream lines, we can have the drawing like this. Here, the black circles are the equipotential lines, and the red circles with arrows would be the stream lines. And if we look at the intersection of the equipotential and the stream lines, we can see they are orthogonal everywhere. The fifth simple potential flow is the flow for a vortex. And the potential function for the vortex would be given as this. Here, capital gamma is defined as positive clockwise. And from this, we can calculate the velocity component. The radial velocity component, UR, is 0, and the tangential velocity component, U theta, given by this expression. And again, we can use the velocity component given here to build the mathematical equations for the stream function, psi, given by this. And we can obtain the stream function psi given by this expression. So if we draw the equipotential lines and the stream lines, we can see for the equipotential lines, for different angular coordinates theta, we have different constant value for the potentials. So the equipotential lines would be the radial lines. And for the stream lines, for different r, we have different stream function. Therefore, the stream lines would be the circle. Now we can calculate the divergence of the velocity vector based on this formula for the divergence of the velocity vector in the polar coordinate. And use this velocity component. We can see here UR would be 0, and U theta would be independent of theta. Therefore, both terms would be 0. Hence, the divergence of the velocity vector is 0. So the flow for vortex would be an incompressible flow. And we can use the formula for the core of the velocity in the polar coordinate given by this. Here, zeta hat is the unit vector in that direction. So we can calculate the core of the velocity vector given by this. And we can see here, this term would be a constant, and UR is 0. Therefore, these two terms in the bracket is 0, and thus the core of the velocity vector is 0. So this means the flow of a vortex is a rotational flow everywhere but the origin. Here we have a look at the circulation of the flow. The first calculation for the circulation including the origin. So the closed curve C1 here, the corresponding circulation gamma 1 is given by this. As we mentioned before, since gamma is defined as positive clockwise, but here the tangential velocity and the increment dl would be same, both anti-clockwise. So this is why the negative sign here. So if we perform this velocity and dl, we have this expression. So the integration would be from 0 to 2 pi, the full circle. Here, dl is defined as this. And we use this definition for the velocity component. We can obtain the expression as this. And we have the result for this circulation. Is actually the capital gamma. The second calculation would be the circulation excluding the origin. So we can make a closed curve. C here, C2 plus C3, and the corresponding circulation would be gamma 2. And we can separate the calculation for the circle 2 and the circle 3 if this distance is infinitesimal. And these two connections, because they are close together and they are in opposite positions, so they cancel each other. And the first term would be same as this gamma, and because C2 is in anti-clockwise direction and C3 is clockwise, so the second term would be minus gamma. So this together would be 0. This means the circulation in the flow of a vortex would be 0 if the closed curve excludes the origin. The same, we can make a closed curve as this, because this closed curve excludes the origin. So the corresponding circulation, gamma 3, would be 0. You can have a check on this if you are interested. The flow of a vortex is quite different from other singularities, for which the flow itself is rotational, but the inclusion of the singularities could generate a non-zero circulation, which would be very important if the lift generation in potential flows is needed, because the lift on a body would be proportional to the circulation around the body based on the Kuta-Yukovsky theorem. The combination potential flows are those singularities in uniform flows, and some of the examples alone can be used to represent the practical potential flows. For instance, the combination of the uniform flow and the doublet can be used to represent the uniform flow past a cylinder. Here, in this talk, the combined potential flow include uniform flow plus a source, uniform flow plus a doublet, and the uniform flow plus an arbitrary body. But how? In this slide, the uniform flow passes the source at the origin. See here. So what the flow pattern we can get for this combination. For the total potential of the uniform flow and the source, we have the expression as this. So this part is for the uniform flow and this part is for the source. So if we write this potential in the polar coordinate, we have the expression as this. Again, the first term on the right-hand side is for the uniform flow, and the second term is for the source. And the streaming function can be given as this psi, and the first term on the right-hand side is the streaming function for the uniform flow, and the second term is the streaming function for the source. So if we draw the streamline for the uniform flow passing a source, we can have a bullet-shaped structure indicated by the red line. The second example is the uniform flow past a doublet. See here what we can get for this combination. The total potential for this combination is given by the potential for the uniform flow, this part, and the potential for the doublet, this part. Again, we can write the velocity potential function in the polar coordinate. That would be given as this. Accordingly, the streaming function would be given as this. On the right-hand side, the first term is for the streaming function of the uniform flow, and the second term is the streaming function for the doublet. And we can write this streaming function as this. Here, capital R squared is given by this. And from this expression, we can see on the circle where R equals to capital R, and on that circle, the streaming function psi would be 0, a constant. That means the circle of a radius R is streamline itself. So if we calculate the velocity component, we can obtain UR given by this and U theta given by this. And we can see from the velocity component on the circle where R equals to the capital R, we can see the radial velocity UR would be 0, and the tangential velocity would be different for different angular position. As such, we can obtain the streamlines of the uniform flow past the doublet. It would be equivalent to the uniform flow past the cylinder. See this plot. So based on the previous two examples, as an intuition for an arbitrary structure in a uniform flow, see the figure, the body here, we can imagine it is possible for us to distribute a number of source sinks in the structure or on the surface of the structure, so that the combinations of all the sources in the uniform flow could form a structure as we expect. So here we have, for the simple combination, uniform flow plus sources. And the question is how we can distribute the sources and the sinks so that the structure can be mathematically expressed in terms of the potential function. Or we have the question, do we need to distribute the sources, sinks in the structure, or just on the surface of the structure? And how we can decide the strength of the sources and the sinks. In the future, we will see from the strict mathematical derivation, it would be shown that the body can be represented by distributing the sources and other singularities on the structure surface in potential flows, which can be determined via the so-called boundary integral equation. I will make talks on this in the future.